Hi, Professor. My name is Chyn. Today I'm going to present about the topic title, which is the segment optimizing maintenance, scheduling of factory equipment using predictive analytics. Firstly, I will talk about the disease, investigate the application of predictive analysis and machine learning technique to optimize maintenance scheduling of factor equipment. Unplanned equipment downtime in industrial setting cause significant operational disruption and financial loss. To address this challenge, the study utilized the segment predictive maintenance dataset and applied the data-driven approach structured under the SHRIP-DM frameworks. A range of supervised learning algorithms, logistic regression, decision tree, support victim management, multi-layer prediction were developed to evaluate based on their performance in predicting equipment failure. These findings support the research hypothesis that machine learning can significantly improve predictive maintenance systems aligned with Industrial 4.0 objective. The study contributes both practical and restructuring downtime and enhanced resource planning and theoretically by validating the machine learning method in a business analytic content. The problem to be studied is that despite the increasing availability of operational data and technologically advancement in machine learning, many manufacturing firms still rely on inefficient maintenance strategy. These firms often fail to leverage predictive analysis efficiently, result in either unplanned machinery downtime or the exclusive allocate of resource toward the maintenance in particular. The challenge lies on identifying the optimized time of maintenance based on the real-time or the historical maintenance data. Current maintenance practice do not fulfill the potential of the predictive analysis, lead to the operational inefficient, increase the cost, and also increase the loss of productivity. The study seek for address this problem by develop the driven data, the predictive model that optimize maintenance schedule using segment predictive maintenance dataset. The first objective for this thesis is to conduct exploratory data analysis on the segment predictive maintenance dataset to identify pattern and correctional related to machine failure. The second objective is to develop and evaluate the predictive model such as logistic regression, random forest, gradient boosting, and the survival analysis that can actually forecast potential equipment failure. The third objective is to compare the effectiveness of the predictive maintenance schedule against the traditional maintenance strategy through simulation model. The fourth objective is to assess the practical implication of the implementing predictive maintenance in the manufacturing setting, including cost-benefit analysis, implementation challenge, and the managerial recommendation. This study adopts a quantitative applied and predictive analysis research design. Quantitative research is appropriate because it focuses on numerical data and objective measures to identify the pattern and relationship. This study rely on large-scale sensor of the data and the need of weighted predictive model using the statistical metric. The apply of the natures, the research obtained from the instance to solve a practical industry problem and plan increment downtime through the developer machine learning solution. The predictive analysis serves as the analytical backbone using the historical and real-time data to focus future maintenance needs in line of trend of industry AI and smart manufacturing. The approach of data-driven, leveraging historical machine performance data to construct the predictive model capable of forecasting equipment failures. Predictive analytics is particular approach for the domain where the understanding of further maintenance need and sustainability reduce downtime and operational defect by focusing on the pattern and the behavior within the data, and the study aim to produce the action insights that support the evidence-based decision making and the enhancement of the maintenance strategy. The data preparation sections details all process requirements to transform raw industrial data into the analytical and usable form, including cleaning, features engineering, normalizations, and the partitioning into training, validation, and test subset. The model developed process developed various supervised machine learning algorithm, logistic regression, decision tree, random forest, and the neural network selection based on their suitability for imbalance, high dimensional, and the time series data. A range of model developed metrics such as accurate precision, recall, F1 score, RCU, AUC rates used to assess the compare model performance, support by the cross validation and sharp-based explainability assessment. The business variable was addressed through a decision integration strategy that links to the predicted output to operational scheduling, reinforcing, and the practice contribute to the study industry 4.0 objective. And then these ethical considerations such as bias detection, transparency, and the responsible AI was also addressed. The truth of this sector conduct to the review is the technologically, methodologically limitation include the dataset, realism, and the developed scope. This component collective established to the rigorous foundation for the presenting, interpreting, and the empirical result into this following chapter. So the finding in the confusion matrix summary showed that 860 of the 890 non-failure instance true negative and 85 of the 110 failure instance true positive. Only 90 normal operational was misclassified as failure false positive and 25 failure of the miss false negative. This performance demonstrates that the model capacity to prioritize real failures with high recall in which is critical in predictive maintenance scenario. Early identifications of true failure case enable time maintenance intervention, minimizing unplanned downtime and operational risk, demonstrate strong classification performance by EX boost, especially for the minor failure case. In the sharp analysis, rather that time since last maintenance was the most influenced features indicating that duration since the previous maintenance strong correction in the failure risk. Lowering temperature and also significantly terminal optimizing earlier that the indicator were. Well, in the ROC curve evaluation, illustrate that EX boost achieved and the AX 0.96 indicate the excellent demonstrative power random forest close to 0.94, while the logistic regression is 0.88, suggests a more limited ability to the discrete failure from the normal operation. This result further confirm the supervised perform the exam method, particularly ES boost, and justify the use of developing real-time precision maintenance in this situation. So on the other side, which is the risk-based maintenance strategy, one of the business key development for this study. So by this strategy, we know that high machinery with the probability greater than 90% of the schedule for this immediate intention, manipulation of unplanned downtime, medium risk precision and addressed in this few days. So allowing flexible of ensure question, low risk equipment continues to the operation under this normal monitoring maintenance resources. So this study presents a significant application for industry. First, the development of the machinery, learning driver maintenance schedule can help manufacturer minimize unplanned downtime, reduce unplanned costs, and extend the asset lifetime. Plant manager can now make the data-driven decision by prioritizing intervention for high-risk equipment, align technique operational can study goal. This system also improve the resources allocation, allowing organization to plan labor and part procurement for more efficiently. This research set out to address the central question, how can predictive analysis be optimized in maintenance scheduling for the factory equipment? The analysis confirmed that machinery learning model, particularly ES Boost, provide a high effective means of the predictive equipment failure based on the historical sensor data. The support of this study core hypothesis, data-driven technique can enhance operational efficiency in manufacturing environment. In relationship to research objective, the study successfully developed a predictive model that achieved over 95% accuracy and demonstrate a strong recall precision. The finding also relied that the failure of pattern are closely associated with the sensor fluctuation, usage duration, and the time since the last maintenance key insight that direct contribute to the precision maintenance strategy. In conclusion, this study successfully demonstrates how predictive analysis and the machine learning can be applied to optimize maintenance scheduling for factory equipment. The ESBO model developed the most accurate precision, while sharp value enhanced the interpretability and user trust. A three-tier risk-based framework was developed to convert model output into the actionable maintenance strategy. All research objectives are met. The study identification real-life features for the application, and the appropriate algorithm will adapt the performance and align result for the operational needs. For future work, research may explore the divide the model in live manufacturing environment to accept the real-time responsibility and the economic impact. Additional exploratory into unsupervised method for the anomaly detection for the model reinforced in live feedback loop, and incorporating external data source such as environment condition could further enhance the enhancement system robustness and the stability. That's all for my presentation. Thanks for the attention. Thank you.